So before I go to diffusion mass transfer, I will first discuss the mechanisms of mass transfer. So last meeting, I already give you the essence and the significance of what is mass transfer and where it is applied to in terms of the unit operation processes that will use its fundamental principles later on. Now, in terms of mechanisms of mass transfer, actually we have the three basic mechanisms of mass transport. Specifically, we have diffusion, we have migration, and we have convection. So the first and the last of these three mechanisms will be the one that will be discussed in unit operation processes. So why will we skip migration? So we will go to that later. So when we speak of diffusion, it is defined as the spontaneous movement of any material from where it is to where it is not. So it is simply saying that the transfer of a material from point 1 to point 2. Simply stated, even if you're not taking unit operation. Now, when we speak of migration, it's the movement of particles, but this time these particles are charged and the movement happens in an electric field. So this explains why this particular mechanism will not be covered in unitary processes. So only the first and the third. The third, the convective mass transport, is the movement of material contained within a volume element of stirred solution. So convective mass transfer most of the time, unlike heat transfer, wherein convection can be natural. In heat transfer, you've learned that convection can be natural or forced. But in mass transfer, majority of the convective mass transfer operations are by virtue of a movement of a stirrer or some mechanical motion that is happening in the solution. But it could also happen by virtue of change or differences in density. So the lighter ones go up, the heavier ones go down, just like in that particular cycle. So it's convective mass transfer. Okay, so we will be discussing first diffusion followed by convection, and this is the end topic for midterm, convective mass transfer. Now, when we speak of diffusion, we have a random movement of molecules from a region of high concentration to a region of lower concentration. So the rate at which a molecule diffuses is dependent upon the difference in the concentration between the 2 points in the solution, which we call this one as the concentration gradient. So the driving force for diffusion is concentration gradient. And it also is dependent on, aside from this concentration gradient, the diffusion coefficient D. Diffusion coefficient D, which has a characteristic value for a specific solution species at fixed temperature. So meaning this diffusion coefficient D is dependent on the species present in the solution at the same time the condition, and specifically it refers to the temperature of that particular solution. So normally the problem gives us this particular diffusion coefficient, or we have a table wherein we can get this one for a particular solution that the problem is giving us. Now, the movement of the chemical species in the case of diffusion is described by Fick's law. Now, there are actually two laws under Fick's law, but we will just be using, even in unitary processes, we're only using the first of the two laws. In Fick's first law, a particle I will diffuse to a cross-sectional area as a function of the concentration gradient, and that concentration gradient is this one, across the selected area. So the flux, which is particles per unit time across the given segment, is expressed as J sub I according to this particular equation. So this one is the flux. We refer to this as the flux, the G sub I. The subscript is pertaining to particle I. Now, in unitary processes, if you're going to refer to soft copies or hard copies of Gencouplys or McCabe, this J has two subscripts. Later on, I will show to you, but this one is a more generic representation of Fick's law. Now, in the more specific version of this, you have two letters here referring to the particle that needs to diffuse with reference to another particle, or to a location where another particle is, or to a distance from a particular location where I is located. So that I will explain later, but this one is generic. Now, the partial derivative of the concentration of I with respect to x, which is the distance, expresses the concentration gradient, and d sub I the diffusion coefficient for particle I. Now, this diffusion coefficient can be estimated, but most of the time it is suggested that whenever we have a table for this one to get it from, then we should get it from the table, because the formulas that are being used in estimating this one, should this be not, shall I say, available, if we will compare to the actual values that are present in the table, is quite the percentage error or the difference is quite big. It's not something that we can not consider as negligible. Now, when we speak of migration, though we will not be using this one, or we will not be dealing with this one in unit operation processes, it's the movement of charged particles in response to a local electric field. Now, the contribution of migration to the total flux is proportional to the charge of the ion concentration, the diffusion coefficient, and the magnitude of the electric field gradient experienced by the ion. A change in the applied potential to a solid electrode in a solution containing ions affects the charge migration as illustrated in the figure above. Now, for increasing negative charge at the electrode surface, if you notice, this one is neutral, so the charges seem to be attracted towards it, both negative and positively charged particles. But once this particular rod is already negatively charged, the ones that will be attracted to it, of course, will be just the positive charges, and the negative one will be repelled. So that is what is meant by the degree of attraction of the charges to this charged, or shall we say, there's already a net potential present in this particular electrode, will determine the value or the number of the molecules that will get attracted to this one. But that's in the case of migration, which will actually be discussed in detail by those who are majoring in electronics and computer engineering. We don't discuss it anymore in unitary processes. The other mechanism that we will also be discussing is convection, the mechanism of convection mass transfer or convective mass transfer. Now, this has something to do with fluids, movement of fluids, which is described by hydrodynamics. So convection, as it applies to electrochemistry, is force movement. So as I've said now, it's force movement of solution species by mechanical steering or by other means. The rate at which a solution is steered can generally be controlled with the convective contribution in one dimension to the total flux of the species described in terms of its hydrodynamic velocity v sub x. The effect of the steering a solution is shown also above. So the figure which has the steering has more, is getting more particles attaching or attracted towards it, but the one which is stationary does not have molecules being attached to it or being attracted to it. So steering in itself enables or enhances convective mass transfer. Now, I will pause the recording for a while. So that's in terms of convective mass transfer. Now, the concept of mass transfer coefficients, which will actually be more easily grasped if mass transfer or convective mass transfer would have been discussed now rather than diffusion, but I need to follow what is dictated in the CMO. I simply took a video for it to be discussed. That way, its essence could be easily grasped by you, since I will not be discussing right now convective mass transfer, where it will be applied to. But later on, after diffusion, after this particular topic on diffusion, we will have convective mass transfer, and that's where you're going to again learn in detail what is the mass transfer coefficient. So I have here shared the concept of the mass transfer coefficient as applied to the mass transfer principle that happens in gas absorption. If you recall, gas absorption, as I have discussed in the introduction, uses the concept of mass transfer. So the video that I have shown here is a video that will hopefully help you grasp the essence or the significance of the concept of the mass transfer coefficient, which should have been discussed first before going to diffusion. The think class with CMO, if you're going to really follow it, there are topics which they dictate in a particular order, but in terms of continuity, there is really no continuity. So it was placed there that the topic that should be first discussed in mass transfer is intro, then mechanism, then mass transfer coefficient. The next topic would have been, as I have mentioned to you already, is convective mass transfer. But what they wrote there is diffusion. So ang daw mautod ka bala sa wala ka continuity kay ging pauna discuss ang mass transfer coefficient nga after pa siya sa topics and diffusion. But nonetheless, if some of you are referring to the CMO guide for heat and mass transfer, this is really the order of the topic. So I just chose this video anyway. I will be discussing it again when we go to convective mass transfer. This is a video from all CHE again regarding mass transfer coefficient as applied to gas absorption. Sorry, class.
An important gas absorption application is the transfer of ammonia to water. A gaseous mixture of ammonia and air is bubbled through water. Let's take a closer look at the process by examining a single bubble. The ammonia is inside the air bubble. There is no ammonia in the water. Since the system is not at equilibrium, some of the ammonia molecules will travel from the bubble through the interface into the water. If sufficient time is available, the transfer of ammonia will continue until equilibrium is achieved. We will use boundary layers to model the mass transfer in these systems. Let's break the bubble into two regions, the bulk region and the boundary layer near the interface. The concentration of ammonia is uniform in the bulk region, but varies across the boundary layer. We do the same thing on the liquid side by dividing the water into a bulk region and boundary layer. In the water, the concentration is uniform in the bulk region, but varies across the liquid side boundary layer. In order to accurately predict mass transfer rates, we need to be able to predict the thickness of the boundary layer and diffusion rates across the boundary layer. And we need to do this on both the gas and liquid side.
Okay, so I hope you were able to grasp for now the essence of the mass transfer coefficient. So it's a determining factor on the degree of transfer of a particular component from one phase to another. But we will again go back to this particular concept when we go to convective mass transfer. So I will stop sharing on this slide and transfer to a slide which is already on diffusion. Can you see this slide on diffusion?
Yes, yes.
Okay, so now we will transfer the diffusion. Now this is the second to the last for the midterm topic. The last one is convective mass transfer. So it's the first of the three mechanisms of mass transfer. That's diffusion. Now diffusion can be described again as a review as the random movement of particles through space, usually due to a concentration gradient. So diffusion is spontaneous and is a result of the random thermal motions between two particles or between particles. The diffusion coefficient D can be solved using Fick's law of diffusion. Now, what is this Fick's law of diffusion? So this is the one that I have mentioned a while ago, that our J asterisk now will have a subscript rather of two letters. That's A. This time we have already included Z. So how do we interpret or understand this particular formula of Fick's law? So your J with the asterisk and the subscript AZ is the molar flux or flux of component A in the Z direction. So the second letter, as I have mentioned, simply points out the direction in which A is moving to. And it is defined by the number of particles that are moving past a given region, divided by the area of that region multiplied by the time interval. So as a result of this, the units for this molar flux of A in the direction of Z or towards the direction Z is kilomole per square meter per second. Why? Because it tells you of the number of particles that are moving past the region. So the number is in kilomole divided by the area of that region, and that's the per meter squared, and divided by the time interval. So that would be your per second here. Your diffusion coefficient or your diffusivity, that's DAB, represents the molecular diffusivity of molecule A in B. So molecular diffusivity of molecule A in B with the unit. So this D subscript AB has a unit of meter squared per second. Now, what about the C sub A? So we commonly represent concentration as C. So it's the same thing in here. Your C sub A is the concentration of A with units kilomole per cubic meter. And your Z is the distance of diffusion in meter, or the distance in meters where your A coming from a certain point 1 transferring to a certain point 2, which has a distance of m meters. So that's your Z, the Z distance, the distance of diffusion of molecule or of component A. So this is our Fick's law of diffusion. And this is the main equation where the rest of the different modes of diffusion is based on. Now, we will first discuss diffusion in gases, followed by diffusion in liquids. The last would be diffusion in solids, which is a little bit comparable to leaching, which you will also be studying later on in separation processes. Now, here we have a simple problem which will illustrate molecular diffusion in a stationary bulk gas. So stationary bulk gas meaning the two gases are not moving in this case, they are stationary. You're given a mixture of helium and nitrogen, and it's contained in a pipe at 298 Kelvin and 1 atm total pressure, which is constant throughout. Now, at one end of the pipe, let's say we'll label that particular end at 0.1, the partial pressure of A, and that's of helium. So let's say A is helium, and that would be 0.60 atmosphere. So notice that the partial pressure of helium, which is supposed to be only P sub A, has still a number 1 after it, noting that that's at 0.1. And at the other end, 2.2 meters away, or that would be 20 centimeters away, we have now the partial pressure of helium decreasing to a value of 0.20 atm. So from 0.1 to 0.2, there is a decrease in the partial pressure of helium. Now, calculate the flux of helium at the steady state if the molar diffusivity of helium to nitrogen, so that's DAB. If A is helium, then B must be your nitrogen. So the other component must be nitrogen. So calculate the flux of helium at steady state if the molecular diffusivity of helium to nitrogen, or that's D subscript AB, is 0.687 times 10 raised to negative 4 meters squared per second. So this one is also given here with a value of 0.687 centimeters squared per second. In this case, you are asked to determine the flux both using SI and the CGS sets of units. So we will have this problem now. So we'll transfer. I'll stop share for now. Go to board. Where's my wait class? I can't see my board. Wait. Okay, I will. Where's my? Okay, here. I have so many things open here. So for our problem, take note that that particular problem did not mention that the mixture of helium and nitrogen is moving. So we will view the movement, the diffusion of helium from point 1 to point 2 as a diffusion through a stationary medium. So both are stationary, actually, the mixture of helium and nitrogen. So we'll go to the given in the problem. I will not anymore show the PowerPoint. I will just get the information from the PowerPoint that I have read a while ago. So can you see my board? Can you see the board, class? Okay. So you're given here a mixture of helium and nitrogen. So that's our system. And this mixture is at 298 Kelvin, 1 atmosphere. Now, this 1 atmosphere is to be viewed as the total pressure of the system already. Now, at one point of the pipe, so this particular mixture is in a pipe. I will not anymore draw the pipe. So from point 1, the partial pressure of helium, so let's say, let's define A as helium, and your B is nitrogen. Your partial pressure of 1, at 1 rather, the partial pressure of A at 1 is 0.60 atm. And at point 2, in the pipe, the partial pressure is 0.2. And it says that you are to determine the flux. So we'll write here the required. You are to determine the flux, and that would be the J asterisk. So of A from point 1 to point 2. So let's say JAZ. And you're given the molar diffusivity. You're also given the molar diffusivity of A to B of helium to nitrogen being equal to 0.687 times 10 raised to negative 4. So this is meter squared per second. If this is in centimeter squared, this would be 0.687 centimeter squared per second, because we're after the flux here both in SI and CGS units. Okay, the problem requires that we express the flux in SI and CGS units. Okay, so this is our unknown, the flux, based on, of course, Fick's law. Okay, we go to the next sheet. We start off with the solution, with the formula that we can use in determining the flux. So based on our PowerPoint presentation a while ago, I will just get the formula. So Fick's law is given as, you have GAZ negative DAB, and that's DCADZ. Now that's a differential equation. So it does not look like a formula where you can do readily substitute what you are provided in the problem. So we will just do the multiplication. So this is just but a separable differential equation. So you will have, sorry, this should be capital class. So transfer the DZ here, and you will have the negative DAB DCA here. And we will have this integrated. So we know that the distance as stipulated in the problem is, I forgot, wait. If I'm going to read the problem, it says there that it will be from a point 0.2 meters or 20 centimeters from each other. So let's say the Z1, Z2 is 0.2 meters. So we'll have this one 0, this is Z1 to Z2. Okay? Or you can write that 0.2. This one will be concentration 1, concentration 2. Okay? If you will integrate, this will be, actually there's a ready-made formula for this, but I'm just showing how that formula came about. So you have Z2 minus Z1, and this would be negative DAB, then you have CA2 minus CA1. Okay? Where C refers to concentration. So this is the thing that we want to determine. So we might as well write a formula that will solve for the flux of helium to nitrogen. So this would be negative molar diffusivity, then multiplied to the difference in concentration over the distance from point 1 to point 2. So this is our formula now. Now in the formula that we have, in order for us to be able to get the flux, we need to know what we need to determine. So as you could see in the formula, we know already this one, and we know already the difference between these two. So we just need to determine the concentrations.